So when we talk about life cycle of a star, this is where we need to know, I said there's a reaction. We need to know what that reaction actually is. Because if a star is just a big ball of rock, it should be able to live forever. But I also know that big rocks don't just give off a whole bunch of energy. Like if it could do that forever, that would violate conservation of energy and we would have a big problem. So we got to think about this life cycle. What's actually going on inside of a star? So if we could zoom in on this and look at a molecular level. If you think back to chemistry, there was helium and there was hydrogen. And hydrogen had one proton, one neutron, that was in the nucleus, and then there was one electron going around like that. Helium had two protons, two neutrons, and two electrons. And so what's actually going on inside of this star here is two hydrogens are finding each other. And these two are fusing together. They're literally like sticking together and changing their nuclear chemistry so that these two things, they have all the pieces, they just stick them together and they make helium. And now because you're actually fusing two nuclei together, that releases a tremendous amount of energy. If you think about like nuclear weapons, that's essentially what's going on here, except it's happening in the sun. So lots of energy, lots of heat being released. So that's the reaction. So the question then becomes, okay, well if there's so much energy being released, like what do I know about bombs? I know that they explode and then they're not all in the same place anymore. Like that's why nuclear weapons go off and then they're done. But the sun has not just gone off and then been done. The sun continues to do this fusion reaction right here. Whoops. So what that must mean is there's still something holding these stars together. Because these things are so massive, they have a ton of gravity, because remember, higher mass equals more gravity. They have a super high gravitational force pulling in on itself. And it's actually that super high gravitational force that causes these two hydrogens to be able to fuse into a helium in the first place. So this gives off a lot of energy, but at the same time, the gravity is so strong that it's pulling on it. Those two kind of cancel each other out. So if we think about it in terms of the fusion reaction wanting to do this, and if we think about the gravity wanting to do the opposite, make it all collapse, what happens is those cancel each other out, that expansive force and that collapsing force, and you end up with something relatively stable in size. Okay, let's do our vocab. When we had just this ball of gas and dust and stuff that we talked about a few slides ago, that's called the nebula. When it gets massive enough, that starts this fusion reaction, and then that causes temperature to increase. When you have that fusion reaction has happened, but it's still collapsing, so they're balanced out, the word for that is protostar. Then, depending on how big your star was, how massive it was, when it started that fusion reaction, it can go one of two ways. So your protostar, that's right here. If it wasn't a ton of mass, it was just enough to start that fusion reaction, it's going to become a main sequence star. So just a regular, like nothing crazy, not a giant. But if you had something that was hugely massive before it started that fusion, you are going to end up with a supergiant. So it's basically, sorry, it says main sequence star with high mass, and then that turns into a supergiant. So we've kind of got the same thing, it's just this one is way heavier, which means if we think about, like here's my planet, and I had, the fusion is trying to make it explode, and then the gravity is trying to make it go the other way. The difference with a supergiant is that those forces are way stronger. So instead of being like this, it would be like that. And like that. I'm hitting the edge of my board here, but these should all be the same. And so what's happening is, yes, it's still balanced, but this is much less stable than something like this first one I drew over here. When one of these reactions stops happening, so if either the fusion stops or the gravity stops, this one on the left is going to have a much more powerful fallout from that. So let's keep working our way through this flowchart. We said you started with your gases, which were just a nebula, was the word. Soon as those got massive enough that you could get fusion to happen, we called it a protostar. If it was low mass, it was a main sequence. If it's high mass, we're going to call it main sequence with high mass, but that turns into a supergiant. If it was the other one up here, so if it was just a main sequence star with low mass, we just call it a giant. Then, what's eventually going to happen is, I'm going to keep drawing this picture, this fusion is eventually going to stop. Because eventually, like we said, we need 2 hydrogens, and those are going to make a helium. Eventually, you run out of enough hydrogen, which means that this reaction can't happen anymore, and all you have is helium. But helium doesn't do fusion the same way that hydrogen does. So, where we used to have all of the gravity pulling this thing in like this, being canceled out by the fusion reaction, well, that fusion reaction is not there anymore. So the picture that we get is just the gravity pulling in on this thing. And if there's nothing to balance it out, well then it's going to shrink. So you end up with shrinking down to that size, and then down to that size, and then down to that size. And eventually, because this has collapsed on itself so hard, you are just left with a tiny, tiny little bit of what you used to have with your giant. And the word that we use for that is white dwarf. Okay, so that was the example with the main sequence stars. If we had a supergiant instead, it basically happens way more. So we're thinking that was when we had a bigger star, bigger mass, so way bigger collapsing forces. Because they're so much bigger, they collapse it way harder. And when they collapse that hard, it sends out a shock wave. Kind of like an explosion has a shock wave, except this is like a super explosion. So we call it a supernova. From there, so that's supernova. If you have, like, let's say it was just a regular supergiant, you're going to end up at a neutron star. And it's going to reach a point where it's relatively stable. It's compressed itself down as much as it's going to. But if you had like a supergiant that was absolutely enormous, it can make what's called a black hole. And essentially a black hole never stops shrinking in on itself. It's constantly pulling itself smaller and smaller, which is kind of hard to think about. So the fancy math word that we use is singularity. which means, okay, we took this thing that was huge, we shrunk it down to the size of a tennis ball. Well, that tennis ball is going to keep shrinking. Now let's shrink down to the size of a grain of sand. That grain of sand is going to keep shrinking. Let's keep going further and further and further until this thing doesn't really take up any space. It's basically just a point that has an enormous amount of mass. So if you think that the Earth has a pretty big mass, relatively speaking, the Earth pulls on you, and like you can't just jump off the Earth. Same thing with a black hole, except it's like way, 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 way stronger. Like to the point that light cannot escape a black hole. So if light can't get there, we obviously can't see these things. But what we can see is if you look at this edge right here, it's called the event horizon. You might have heard about it in the news a couple years ago. Basically, what we do is we take a beam of light and we shine it like that. And what we see is that the light doesn't just keep going in a straight line like we would expect light to do. It actually kind of gets pulled in towards the black hole. So then it goes like that because it's still being pulled in like so. And when it gets to this point right here that we can no longer see it, that's where we know that the black hole is pulling hard enough that light cannot escape. Okay, so when your helium reaction is totally done, like we were slowing down, I know I drew the arrows going away completely. It should have just been they're slowing down, and so it gradually shrinks on itself. Eventually, this reaction is going to completely stop. What happens is it shrinks, you get a white dwarf, and then this thing cools down because there was a ton of heat on it from that fusion reaction. After it cools down, it becomes black, so we call it a black dwarf. With the supergiants, it works a little bit different. It keeps collapsing, and it's happening so hard that it sends out that shockwave. That's what we call the supernova. And then you're not left with any of the gas like around here anymore. You're only left with the core, so that's a neutron star. If you have a really, really strong supernova, that's where your black holes come from. We kind of already talked about this. So there is your life cycle of a star. I know there's a lot going on here. I'm hoping we went through it in enough detail that it doesn't look super intimidating, because you should probably know this stuff. And now we're back to where we left off